everyone. I'm going to talk about the time series analysis I performed from the three of the data from Edward Equifor. The first data is J17 index well data, Komal Spring data, and San Marcos Spring data. The data are downloaded from the following website. First I read the data. Since the data did not have the time series of dates, I created a sequence of data from the start to end date, and then change the data column of the data to the date format and merge the two data so to convert it into a time series format. So after the data was converted to time series, we checked if the I checked if the data has some missing values, and while checking the missing values, there was 800 not any values. So to filter them, I used Kalman filtering. For the Kalman filtering, I used any underscore Kalman function from the ImputTS library. The struct.ts means that it uses structural time series model, and smooth equals to true means I'm performing the smoothing along with the imputation. The max gap equals INF fills all the gaps in the data, and so after performing the Kalman filtering, again I check the summaries of the summary of the data. So we can see that here the any values have been removed. Also the mm, um, mean medians have also changed, but the change is not like it's small, so we can ignore it. And then after that I performed a rolling mean for 10 days moving average. Mm, After doing that, I use the plot function to plot the time series plots between water elevation and it. The daily water elevation series has some missing values, and after the um, filtering and the 10-day moving average, we can see that here the missing values have been filled up, and also the um, data have been smoothened because we did a rolling mean of 10-day moving average. What it does is it uh, takes data from 1 to 10 and takes a mean and gives a mean value, and similarly does 2 to 11 and gives us the mean value. So after that I performed the autocorrelation function and partial autocorrelation function for the 10-day moving average data. The ACF shows correlation of time series with their own lagged values, where partial autocorrelation function shows the correlation with their own lag values, but after removing the intermediate lags. The autocorrelation plot shows how much our time series observation depend on the previous observation, and the mm, uh, partial autocorrelation function gives us the effect of past observation on our current observation. For the um, lag of the both the autocorrelation and partial autocorrelation, I have used 800, which means around 2.5 years. After that, I looked upon the trained, seasonal, and random data of our 10-day moving average. Mm, the observed means it gives the observed value, and the trend shows us the trend of our data, and random means the noise, which also means the unwanted data from our data. Then I perform the Mann-Kendall test. Mann-Kendall test is a statistical test which gives us, which helps to detect the trend. Here, tau is the Kendall's rank correlation coefficient, and P represents the probability of representing null hypothesis. And the positive tau gives us the increasing trend, while negative gives us the decreasing trend. So since our data has a negative tau, it has a decreasing trend, and we also have extremely small p, which means the null hypothesis of the trend can be rejected. The Mann-Kendall test suggests that we have a decreasing trend in our data. So I also perform the same process for Komal Spring data. The Komal Spring data had 195 um, NA values, which was removed in the, by using Kalman filtering. Also, um, the 10-day moving average was also performed for Komal. And then here for Komal also, uh, I did the same autocorrelation function, but and use the same lag. Also, the Mann-Kendall they showed that the data for Komal string also has a decreasing trend. For San Marcos Spring data, also I performed the same process, and but the San Marcos data had only one missing value. Mm, Also, for San Marcos, I changed the lag value from 800 to 400, which is around 1 year. Our tau for the San Marcos is positive, which means there is a slight increasing trend in our data for San Marcos Spring. So after performing all the autocorrelation and partial correlation for all the three datas, I took the uh, the datas for from these three datas to perform cross correlation function between these datas. Uh, the cross correlation function is a measure. It measures the similarity between two time series datas. It gives a correlation coefficient between two time series at each time lag. So for um, the I perform the cross correlation function for each by taking like first water elevation and discharge for um, Komal water elevation, and then discharge for um, San Marcos, and then cross correlation for the discharge of Komal and um, uh, San Marcos. I kept the lag value of 200 for all the three cross correlations. So from cross correlation, we can see that the positive cross correlation, the positive values of correlation coefficient shows that the correlation between the two time series is positive, and negative correlation coefficient shows that the relation between the two time series is negative. The zero value shows that there is no relation between the two datas. Thank you.